Hey everybody, today we are going to be continuing on with Hess's law. So last time we learned that we can manipulate given reactions and that will impact the delta H value of a reaction. Now what we can also do, those reactions are built from formation energies. You can find those formation energies on page 4 and 5 of your data booklet. And we can use that to find individual entities of a reaction. Okay, so what the heck am I talking about? What I'm trying to say is our first learning goal is going to be delta H, or enthalpy. Change in enthalpy can also be determined by taking the sum of delta H formation of your products and subtracting them from the sum of your formation enthalpy change of your reactants. The formula looks like this. Delta H of a reaction is equal to the sum of your products, of sum of your delta H formation of your products minus the sum of your delta H formation of your reactants. Okay, so here are our goals. Identify the molar, oh, that is a very interesting looking M, molar enthalpy, so your delta H, of one of the entities in the reaction. So basically an entity is either one of your products or reactants. You're either one of your compounds or your elements. Here's the method. You're going to use, so sometimes they provide the values for you in a test question, but most of the time you're going to have to use pages 4 and 5 in data booklet to identify your H formation, delta FH of compounds. Then, now sometimes anything that is in elemental form, so any entity in elemental form will have a delta H formation that is equal to 0 kilojoules. Okay, and then lastly, we will use the formula. I forgot to put the formula. Delta H is equal to the sum of your formation of your products minus the sum of your formation, delta H formation of your reactants. Okay, so let's do an example. Given the data below, determine the molar enthalpy of D using the following reaction. So most of the times they're going to give you reactions that are already balanced. I know in this case, these are just random compounds. It's just to help you learn how the formula works, and then we will go into balanced reactions after that. Sorry, into proper reactions after that. So I'm going to just work on the side here. Our formula, delta H, is equal to the sum of heat formations, sum of enthalpy of formation of your products minus the sum of enthalpy formation of your reactants. Okay, so we're going to pretend like this is representing page 4 and 5 in your data booklet. So it'll look exactly like this, and then it'll list the values of all of your entities and compounds. Okay, so basically, this number goes here, negative 125 is equal to, now, this is in kilojoules per mole. So we're going to set it up like this. Delta, so the sum means to add. Our first product, I'm going to do all the products in green. Our first product is 2, and then we're going to take our our change in delta H formation for the compound B, plus 1, so I'm not even going to write that, plus our delta HF of D, minus, I'll do that in red, minus bracket, our reactant, so 2A, so delta F H A, sorry, it takes me a little bit of a time to process it too, plus 3 delta F H C. Okay, so I want to show this to you because it's the full way, but I kind of have my little shortcut methods. Okay, so in the blue, in the green, we're doing our product. So we have 2B, that's our first product. I have plus 25 kilojoules per mole. I'm going to multiply that by 2 moles. Okay, I'm just going to do it down here. So B, delta formation, sorry. So B is going to be 2 moles times by positive 25 kilojoules per mole. Mole cancels out. And that gives me 50 kilojoules. Okay, so this, let's start plugging this in. 125 is equal to 50 kilojoules. Okay, and if we want to keep those units in to help us, we can. Plus, okay, now D. D is what we're looking for. Okay, we're looking for our heater formation, sorry, our enthalpy change of formation for D. So I'm going to leave this one as is. Minus, okay, so now 2AD, 2AD, 2A delta formation H is equal to, we're going to take our A, which is 2 moles of A multiplied by negative 10 kilojoules per mole, which gives me negative 20 kilojoules. So in my brackets, this is negative 20 kilojoules plus, okay, the next one, we are looking at C. So C, do down here, 3 delta FH of C is equal to 3 moles times by negative 5 kilojoules per mole. Moles cancels out. I'm left with negative 15 kilojoules. Negative. So instead of the plus sign, I can put negative 15 kilojoules. All right, I'm going to do my isolations now. So we have 100, negative 125 kilojoules is equal to bracket 50 kilojoules plus delta FHD minus, let's collect this. So negative 20 minus 15, that gives me negative 35 kilojoules. Okay, negative 125 kilojoules. Let's open up that bracket. Okay, you open up a bracket by seeing what's in front of it. So there's just that invisible plus 1 there. Anything multiplied by 1 is itself. Negative 1 times negative 35, that turns it into positive 35 kilojoules. Okay, let's collect these two. Negative 125 kilojoules is equal to 85 kilojoules plus delta FHD. Now let's isolate for this one. I'm going to subtract 85 kilojoules on both sides. Subtract 85 kilojoules on both sides. And that is going to give me 200 negative 205 kilojoules. Now, I forgot to add this in, but there's an invisible 1. Okay, so here we need molar. So in order to put it back into this table, we need to divide it by moles. Well, there's 1 mole of D. So delta FHD is equal to negative 205 kilojoules divided by 1 mole. So that would give me negative 205 kilojoules per mole. And that would be my final answer. Okay, so that's what I have for this lesson. You can go ahead and do the practice questions, and we will be back in class to do the warm-up and lesson.